Yeah. Hello. So thank you for a kind introduction, and thank you for inviting me here for this presentation today. Thanks for coming to listen. Yes, today I will present one of my research activities, the results for these activities about quantum dot-based, titanium dioxide quantum dot-based photochromic materials for smart window applications. Shortly about myself, I am currently, this was actually wrong information you introduced, because I am currently the director of the Institute of Materials and Surface Engineering, and this laboratory doesn't exist anymore, but these changes were like half year ago. Yeah, and by myself, I'm leader of several scientific projects, attracted considerable amount of funding for research. I'm leading 6 postdocs students. I have scientific papers, close to 100 and so on. So you can, this is my short summary about me, and this is the short summary about the Institute of Materials and Surface Engineering I'm leading. This is which there are the 3 main main activities in this institute: functional materials, inorganic materials, and biomaterials. And basically there are located 3 professors, 9 postdocs, and 5 PhD students. And so yeah, this is the key infrastructure. We have really nice, sophisticated techniques for characterization of the materials and so on. Okay, I have several, as I mentioned, research activities, and here I want to demonstrate all of them, and then I will switch to the topic of today's talk. So basically, I'm working with different materials like triboelectric generators, which are used to convert mechanical energy from movement, for example, or noise to electrical energy. I'm working with the materials for antimicrobial coatings and photocatalysis, for water purification. We are working with materials for these smart window materials applications, and also gas sensors for environmental monitoring. And also we have a topic which is really new, and we get in really nice journal published about this amphoteric decoupled electrolytes, where we can basically split water without using the membrane in electrolyzer. This is new. I'm wondering, do you see the pointer, laser pointer on the screen? I think not. Yeah, about today's topic, why it is important. It is important that because we can control we can save energy by controlling the infrared light transmittance from solar, and this is like considerable energy. If they would install the smart windows in the skyscrapers, then they could, in the United States, they could save 1% of energy consumption. This is because you don't need to use your air conditioner so much to cool down your room. And this is also important for greenhouses, where there's a lot of plants and fruit are like just burning out in the sun. And if you could control this transmittance, infrared light transmittance, then you could save up a lot of group basically. And yeah. And the important thing, what to tell here, is that we need to maintain the visible light transmittance, but we need to so we need to see through, and also plants need their light for photosynthesis. But what we want to block is to block the infrared light, and this is also the thing we are focusing to develop these materials that can control this infralight transmittance. And at some seasonal conditions, you actually want to let this infrared light from sun into the room, so it gets warmer. So you need to have some kind of possibility to control this transmittance also. And there was a paper published already almost 10 years ago in Nature, where they proposed such smart window device. This is still a benchmark in the field. Basically, they used glass matrix, niobium glass matrix with indium tin oxide degenerated semiconductor quantum dots in there, and then the lithium ion intercalate in this layer, and in such a way you can control the charge carrier concentration in these nitro nanocrystals, and this in turn influence the optical properties. So, but so far this concept is not commercialized, not in the market, because as I told already, indium tin oxide crystals, niobium glass matrix, because it must be conductive. It also there is lithium in the system, so this is like expensive electrochromic device, and also to keep it transparent you need to apply some energy or to color it. And yes, and we started in 2018 when I was this was started earlier actually, when I was spending my time in University of Tartu, where we developed photochromic titanium materials which change their color when you irradiate by light. So as you can see, it turns pitch black, and you can turn it black back to the white. And this here, the transparent liquid is actually composed with the solid nanoparticles, but they are so small that they don't scatter the light, and it looks like pure water. So they are really small. This is like 20,000 times smaller than diameter of hair. So, and the mechanism for these materials is so that if you have a light shining on in these particles, there will be induction of electrons and holes, and these holes are scavenged by the other organic molecules into the liquid. So, and this electron population in these particles are changing the properties. So this in short. And so we can change the properties, transmittance in a broad wavelength range, as you can see. So this is the curve when it is transparent, and it becomes untransparent. This is light transmittance on y-axis. So, and yes, and we can do it for many cycles. Further, after this work published in 2018, we developed material which switch much faster. Those particles I shown change their color in 1 hour. Now we can make it in 120 seconds. So we tune our nanoparticles. You probably don't need to pay attention to these graphs, but what they show actually is that there is a rate constant extremely large at the infrared range, and this means that we have a strong response for these nanocrystals, especially in the infrared range, exactly what we needed to control infrared light transmittance. And we also, in the further development, this was published already this year, we made it in a gel-like material, so you can fill the cell, because you can't use liquid because this solvent, because it is evaporating, make bubbles in the cell and so on. So we developed gels. We developed gels for these smart window materials, and also these gels are responsive, as you can see, that transmittance is changing and so on. And yes, and although these gels the results here are presented for pure titanium particles, but we developed based on niobium doped titanium dioxide particles. We developed also the electrophotochromic device. This is our next step. So this will, if we would use without the electrodes device, then we can't like switch off the color change, because color is changing when the light is irradiating, but we want to turn it transparent at some point. And then we made such device. There is this gel layer with niobium doped titanium dioxide particles between conductive transparent electrodes, and there we have in the system also redox mediator. So when the electric chain up and up, you see it is open, then it becomes dark, and when you close the electric chain, then the mediator at some potential is reduced, turn it back to initial position, and in such a way also this is the gel layer get transparent again. So yeah, this device we have developed so far. Here we have some results. This is when we this laser is not visible on screen. This is in the first 10 minutes, you see that this is in visible range and this is in infrared range. This invisible range, you see that transmittance maintains something like 30%, but it's actually enough to let visible light through. Of course, we would like to see that there is no change in visible range at all, but at the same time, we have a complete cutoff of infrared range. It's starting from 700 nanometers. So this is a whole way to go, I would say. And we also need to develop this gel matrix because due to the stability issues, but yeah. But as soon as we get that done and maybe tune a little bit more our particles to be more selective to infrared range, then we are good to go, I would say. So yeah, that's all. Thank you for your attention. Here are some collaborators on the slide, and thank you for listening, and I will be happy to take some questions. Thank you.